Hi guys, BuildZoid here, and today we're going to do a PCB breakdown of my most recent GPU acquisition. This is a GTX 680. Actually, technically it's not the most recent because it turned up before a different card, so I actually have a card that's even newer to me. But I did technically buy this one. This was my most recent purchase, even if it's not necessarily the first card to turn, the most recent card to turn up. Anyway, this is a GTX 680 Lightning. I picked it up on eBay for 55 quid. I think somebody didn't know that, like a regular GTX 680 goes for around that price, and this is a Lightning. So I think that like an absolute steal in my opinion, because this is a really, really nice custom card. Unlike, say, the new 2080 Ti Lightning, which is basically it's basically a reference card with bolted on LN2. Well, they didn't even bolt them on that well. They're kind of missing LN2 overclocking features. But anyway, let's take a look at this thing right here. So obviously GTX 680 core, 2 gigs of GDDR5. I'm not sure if there was a 4 gig version of the Lightning. If there was, then I want to get one of those as well. But anyway, up here we have a dual BIOS switch. So the card has an LN2 BIOS. And then, of course, the highlight of the show for this card is the VRM, that's our V-Core, the larger of the two, of course, because V-Core pulls more power than VMEM. And then above that, we have the memory VRM, so that's our VMEM. And I guess let's just take a closer look. Let's just get right into these and cover all the other features on the card afterwards. So, starting off with the more important of the two, V-Core is a 1, 2, 3, 4, 5, 6, 7, 8 phase, and that is a real 8 phase. So yeah, like which is pretty awesome. So proper 8 phase controlled by this chip right over here, which is a CHL 8318. So that goes up to 8 phases. This was kind of the standard high-end voltage controller for NVIDIA and Kepler NVIDIA cards, as well as I think some Fermi cards, because you really couldn't find a controller that supported the NVIDIA voltage regulator standards that also was like good other than this. So, there's a bunch of cards using the CHL 8318 because that's kind of the only option. So here it's running as an 8 phase. So, all the available phases are used for the V-Core VRM. And the driving situation is, broke GIMP. So if we go to the back here, you might notice that there's only 4 drivers and also the rest of the low-side MOSFETs for V-Core. So I'll just put an L on the, well, yeah. So that's the rest of the low-side MOSFETs right here for V-Core. But we have only 4 drivers right here, right? But these are International Rectifier 3598s. So they're not one driver, they're actually 2 drivers built into one chip, and there's an optional doubler function built into them as well. That's not being used here. So what you have is the CHL is somewhere over there, right? Yeah, it's somewhere over there. You basically have 2 PWM lines go into each of the IR 3598s, and then that just drives 2 independent phases. In fact, the 3598, it is literally 2 drivers in the sense that if you had 2 different voltage controllers, you could have one phase on from each of the controllers. Like you could have 2 different phases, but controlled completely completely separate regulators driven by one 3598 because the drivers can run completely independently. So it's basically like having 2 CHL. Well, it's not as strong as a CHL 8510. A CHL 8510 is a faster, more powerful driver, but for all intents, configurability from a sort of configuration perspective. And a logic perspective, this is functionally 2 CHL 8510s and a doubler that's in front of those that you can choose to use or not use. So, yeah, this is a proper 8 phase, and these are just dual drivers. Also, an interesting thing that MSI has on this card is there's actually LEDs to indicate running phases on the card. So this is actually something I've wanted to replicate for like a reference card of my own choosing, but the last time I tried it, it didn't work. properly. Like, it didn't work the way I wanted it to, and I'm not sure why. I think I screwed something up with it, but anyway, so one day I'll figure that out. But here it is, you know, the card comes with LEDs indicating which phases are running, and they also have that for the memory VRM up here. There's no extra low sides because, well, memory doesn't really need that much power. So if we go back to the front of the card, now let's take a look at closer look at the MOSFETs. So here we have another low side MOSFET and a high side. So each phase has two low side MOSFETs. And the reason why you would put two low side MOSFETs is really simple. The low side MOSFET handles the bulk of the current going through the VRM. You know, if you're at like 1.2 volts output, then the low side MOSFET is going to be handling like 90% of the current going through the VRM, roughly 90, not exactly, but pretty close to 90%. And so, one of your main sources of sort of power loss in a VRM is going to be just conduction losses through the low side MOSFET. So one of the easiest ways to get better better per phase efficiency is to get lower RDS on low side MOSFETs. Now, the thing is, at some point, you're going to run into the issue that they don't make better low side MOSFETs. Like, there's pretty much, I think the best you can get is like in the range of like 1 milliohm RDS on for your low side MOSFETs. So what MSI's decided to do here for the low side is they're actually putting two low side MOSFETs in parallel to get an even lower RDS on than normal, and these are IRF 8304s, and those are direct FETs, which you can tell from the packaging right there. And so there's two of those in parallel, and I think, well, I didn't put it in my notes, but I want to say these are like 1.7 milliohms at 10 volts gate to source voltage. So that's low. Putting two of them next to each other is lower. So this is like the end result is this is really, really powerful on the low side. And then for the high side, MSI opted for the IRF 8327. This is still a direct FET, smaller packaging. What's worth noting about these direct FETs is, if I remember correctly, it's the drain. Is it the drain? Yeah, it's the drain. So you have these have an exposed drain. So essentially, the reason why you need to keep that in mind is it's they're electrically hot. So they can, like, if you put a piece of metal between here and here, that'll short your phases out. You don't want to do that. So that's something to sort of keep in mind with direct FETs, is like you have to have a thermal pad and some kind of non-thermally conductive thermal pad. I mean, non-electrically conductive thermal pads, because yeah, these are not they're not insulated. They're not grounded or anything like that. So, but what it does do is it actually makes it really easy to probe the switching frequency of a phase, because you just stab one of the MOSFETs and bam, you can see the phase running. If you have an oscilloscope. If you have a multimeter, you're not actually going to see anything. It's just going to tell you the output voltage pretty much. So anyway, so yeah, and the IRF 8327 for the high side, and I didn't write down any notes about this thing, but if I remember correctly, like, this is pretty, like, it's a pretty fast direct FET. IR definitely makes some slower ones as well. So the end result here is that this VRM actually gets some really awesome efficiency. Now, one thing worth noting compared, like, with my efficiency figures for discrete MOSFETs like this, instead of straight up power stages, is that if you take like when I'm doing my VRM efficiency calculations for power stages, those factor in the driver power requirements, which basically it takes energy to switch a MOSFET on and off, even if you have no current going through the MOSFET. When I do discrete MOSFETs like this, I do not account for that power loss. So what ends up happening is, if I have a VRM like, say, this 8-phase right here, at low current outputs, it's going to look really, really efficient when it shouldn't, because there's going to be like 1 or 2, maybe 3 watts missing from the overall power consumption of the VRM, because I'm not accounting for the driver, like the drive power loss. So that's just something to keep in mind. And I'm pointing that out because this VRM, when we start listing off the current figures, there's a few of them where the efficiency is over like 94%, and it's just like, no. Like, that's not, no. The top of the line power stages don't do 94%, you know, in this kind of configuration. And generally, top of the line power stages are going to be more efficient than anything you can throw together like this with discrete MOSFETs. Though, I don't know. It might be possible that is this. Well, no, because if I scaled the current down lower, eventually the efficiency would just keep going up and up and up. So, yeah, that's one of the downsides to the way that I do the power losses for discrete MOSFETs is just I'm ignoring like, it's not a lot of power loss. It only really matters when you're looking at very low current outputs on a VRM with way too many phases, because you have, like, you know, a fraction of a watt per phase that if, you know, that's the reason why you normally wouldn't run 8 phases for 10 amps current output, because it wouldn't be efficient. But your conduction losses would be nothing, your switching losses would be basically nothing, and all of your energy being used by the VRM would be just from the driver turning the phases on and off. So anyway, did want to point that out. So for 1.2 volts output voltage, 300 kilohertz switching frequency, and a drive voltage of 10 volts gate to source, which I'm not sure that MSI is actually driving this with 10 volts. Because there are two, like, the thing is, 3598s, in a lot of cases, like, the 3598s support running off a straight 12 volts, so MSI could just feed 12 volts directly into them, but the thing is, there's these two LDOs right here, and I've not yet powered on the card, so I've not had a chance to check if MSI is driving this with, like, 12 volts, or 10 volts, or 7 volts, or something like that, so, yeah. Anyway, we're just going to assume it's 10 volts because that makes this VRM look better, and it's a Lightning, and I want to believe that the card I bought is amazing. So we're just going to go with that. Well, it doesn't really matter. Like, if I did the ratings at 5 volts, the efficiency would be worse, but it ultimately wouldn't change the fact that this VRM is a ridiculous overkill for a GTX 680 anyway, so it wouldn't really make much of a difference. So let's get right into it. 150 amps output on this VRM would produce about 10.5 watts of heat, not accounting for drive losses, because, yeah, that's just conduction and switching losses through the MOSFETs. And this is the figure where it's like, yeah, if you do the math for this, then you come to the conclusion, hey, that's like 94.5% efficient, which is really, really good. Except those IR3598s on the back of the board, they burn power too, and I'm not accounting for that. And that's making this figure look way better than it should. Anyway, going up to 200 amps, like, this becomes less of an issue as we go up in current output, because it becomes less and less of a factor for the overall heat output of the VRM. So anyway, going up to 200 amps, VRM is going to be producing about 16.5 watts of heat. So, like, honestly, you should be able to run this card without, well, yeah, without a heat sink, but maybe just some airflow over the VRM at 200 amps output. Like, you should have no problem with that. Then going up to 250 amps, you'd be looking at about 24 watts of heat output, and going up to 300 amps, about 32 watts of heat output, and then 400 amps, 53 watts of heat output. Like, this VRM is just ridiculously efficient. And that's what you would expect from a Lightning card, right? Because this is like an extreme well, actually, the thing is, there's actually, like, other Lightnings which aren't this ridiculously overbuilt, because the thing is that effectively the conduction losses in this 8 phase are kind of like if you had a 16 phase. That's basically what's happening by putting the two of these in parallel. Now, admittedly, they might not be driving them at straight 10 volts, and if they aren't, then that conduction loss would actually go up, which I guess at the 400 amp current, 400 amp output would actually make quite a difference. Since at this point, like, your main source of power loss is the conduction losses through the low side, but yeah, that's still, like, it wouldn't be, like, still, it's a GTX 680, right? Like, efficiency at 400 amps is basically irrelevant. I don't think these cards hit that, even if you're on liquid nitrogen. So, Yeah, lovely super overkill 8-phase V-Core VRM right here from MSI. I mean, what's not to like? It's a Lightning. It's a Lightning before NVIDIA made NVIDIA cards suck. Well, made NVIDIA overclocking cards suck. That's one thing I guess. I guess a lot of people might not be aware of this, but like MSI had a really like pretty heavy extreme overclocking program. Like they organized MSI Overclocking Arena tournament, Overclocking Arena, which was basically a big overclocking event. They would fly in like 100 overclockers, and you know they would just bench and try to break records, and it was all about just getting MSI hardware to be better at extreme overclocking. And then not that long ago, well, a couple of years ago, they basically scrapped the entire extreme overclocking focus that they used to have, and the end result is that you know, you don't get cards built like this anymore. You still see the branding, and you get mini ITX motherboards that for no apparent reason are really damn good at memory overclocking, but you don't get proper Lightning cards like this, which is, in my opinion, a real, like, I think that's a real loss, but at the same time, I totally understand why they did it, because you know how you make how do you make a more appealing product to consumers than making a nicely built high quality GPU? You put gaming in the name, and it'll sell. It doesn't even need to be very well built. Just put gaming in the name, and it'll sell more units than any other thing you make. So yeah, and that's kind of what ended the extreme overclocking program at MSI. The other thing is NVIDIA actually started getting really obnoxious. MSI originally released this GTX 680 actually originally released with like a proper extreme overclocking BIOS, and then after a few thousand units produced, I think NVIDIA was like, no, MSI, you can't do that. You can't ship these cards with this extreme overclocking BIOS. You need to put a locked down NVIDIA approved trash BIOS on the cards. And so yeah, and NVIDIA kind of also had a hand in making the Lightnings steadily less impressive. But 600 series, like the 680 Lightning, you know, in my opinion, probably, well, the 780 Lightning was still a proper Lightning. It's just, it was already showing signs of scaling back because NVIDIA was putting more and more restrictions on what the GPU vendors could do. And then you get like the 780 Ti Lightning, which because of NVIDIA ended up only being like an engineering sample card, never got released to the public. And then you had the 980 Ti Lightning, which just straight up didn't compete with the other extreme overclock. Like, actually, that one didn't do that badly, if I remember correctly, but it didn't really match the other 980 Ti's out there. And then you got the 1080 Ti Lightning, at which point it was like, well, that's not a real Lightning. it has the name, but it's not a real Lightning. And now you got the 2080 Ti Lightning, where it's like, it still has the name, and it's even less of a Lightning than the 1080 Ti before it. So, yeah. Anyway, moving on to the memory VRM. 1, 2, 3 phases controlled by a UP 1612 voltage controller over here. So that's a 3-phase. I can't actually really get any information on this chip, but it's 3 phases. And memory power delivery requirements, especially for just 2 gigs of GDDR5, aren't really that stressful. Didn't stop MSI from building a 3-phase, didn't stop them from using the same low-side and high-side MOSFETs as they used for the V-Core. So this right here, we're not even going to talk about it. I mean, ridiculous overkill. You don't need to do any math to know that GDDR5, like this powering the GDDR5 is ridiculous overkill. So, yeah, no surprises there from MSI as well. I mean, 3-phase, like, it's kind of funny. 3-phase GDDR5 power for a lot of extreme overclocking cards from like EVGA and I think MSI ran 3-phase memory power for a ton of their cards. And then you have Asus, who normally just goes for 2-phase. So, yeah. Anyway, so 3-phase memory power, ridiculous overkill. Most of the bulk output, bulk capacitance for this VRM is not on this side of the card. It is there. Most of it's actually on the, like, all of it's really on the back, right here. Interestingly enough, they also have these little tantalum polymer capacitors in the, so these are aluminum polymers. These are tantalum polymers, and these are 220 microfarads each. But I tried to look these up, and as far as I can tell, these are really not that impressive, as they seem to be a series of capacitor from Panasonic that's like 30 milliohms ESR or something like that. I should have really written that down in my notes, but then I was like, I'm not going to mention it, and then and now I'm like, I'll mention it anyway. So yeah, 220 microfarads. So there's some more bulk capacitance over here, but it's just like that's really high ESR. So normally you want your output filtering to have low ESR, but I guess they really just wanted to jam a bunch of output capacitance. And the thing is, they also just have a bunch of multi-layer ceramics, and I'm not sure if that's stock because I haven't seen a reference, like I haven't looked at a reference GTX 680 in ages, but this looks a little bit more than what I'd expect from like a reference NVIDIA card. So yeah, you also have like like this group over here and this, and so the memory output filtering, I mean, like nothing, not really like it. It looks like they put a little bit more effort into it, though I do wonder why they decided not to go with the extra bulk output on the other side of the card, because it's like, you know, they've done kind of everything else. The VCore VRM is missing one, like a couple bulk, a couple capacitors all the way up here. But if you look at how the power plane is shaped, that's like the least important spot in the entire VRM right there. Like, I'm assuming that the power plane literally just goes like that, and there's no connection going through that area, because if there is a connection going through that area, then that should have probably stayed. Anyway, so yeah, and then, you know, more aluminum polymers, some multi-layer ceramics in between that. So, quite frankly, this output filtering section on this GTX 680 Lightning is more to my liking than what you see on the 2080 Ti Lightning. So yeah, I mean, they don't build Lightnings like they used to anymore. But the other thing that's kind of interesting about old Lightning cards is this thing. So this right here is what MSI calls the GPU reactor. And it's basically a bunch of capacitors on a little add-on card. Now, I really don't like this. Like, this is a good idea on paper, but there's just one issue. And that's also this also enables a bunch of this does enable some overclocking features, if I remember correctly. And it also lights up. There's a bunch of LEDs on it when it's installed, but that's just fluff. That's just useless fluff. But what I don't like about this reactor thing is this right here. It's a cool idea to try cram more capacitors behind the GPU core. Like we all know how much I love putting capacitors in places where, you know, you'd think you can't physically fit any more capacitors, but can you? So, you know, I'm a huge fan of extra capacitance. The thing is, the way that reactor hooks up is these little connectors, and those are some very, very, very little legs. And kind of the main benefit of, you know, SMD capacitors like this, like where they get their huge ESR and ESL advantage over, you know, your usual CAN types. Well, they don't even have a massive ESR advantage. It's usually just ESL. Like, you can get aluminum polymers like Nichicon makes RR5 series FP caps, which are 5 milliohm ESR. So you can get some ridiculously low ESRs in your CAN type, like CAN polymer capacitors. The thing is, you can't get anywhere near the ESL, which is the equivalent series inductance of an SMD capacitor, because your CAN types have legs, and these don't have legs. These have little tabs that just solder directly to the board. And that's a huge, huge part of why these are superior for output filtering compared to, you know, your CAN type aluminum polymers. And, well, the GPU reactor thing kind of defeats the purpose of that with the little legs. And the other thing about so the thing about the little legs is, like, they'll add extra series, equivalent series inductance. The other thing is, because these are so thin, and also because they are literally, like, they're just touching the connectors. Like, this is just it's a connector. It's not soldered on. So the resistance the contact resistance there is going to be completely screwing over those capacitors. Like, I really, well, actually, as far as I know, that reactor literally does nothing for your overclocking range on the cards. And, you know, it's like, I can't say I'm surprised, because that's a lot of capacitors trying to, you know, work through very, very few kind of flimsy looking legs as their electrical connections. So, yeah, I think good idea, but the implementation I think is lacking. And the thing is just if you wanted to add more bulk capacitance to the GPU core, you have a power plane going through right here that I feel like if you just filled this area, and maybe, like, yeah, you could totally go like, bam. Well, I don't know, like the memory power plane. Actually, I think this might be a ground fill right here. If that's a ground fill, which it might be, like if that's a ground fill right there, then bam, like just put them like that, and just have ground, just, you know, put your mark like that, and then I think there might be a ground tab over here or here, so I don't know, squeeze a cap like that, right? Just put all the capacitors that are on the little GPU reactor thing, just put them on the freaking power plane. Just cram them as close to the core as possible, because that's kind of the idea. You want to get them really close to the core, but if you're gonna put them behind these flimsy little connections, you've just, like, you just ruined all the beneficial properties of SMD capacitors by doing that, as far as I'm concerned. So, yeah, I mean, you know, it's an interesting feature, but as far as I know, it never really worked that well, and eventually they stopped doing it. So, and I can't help but wonder why capacitors behind, you know, physical connectors like that couldn't work. Because the thing is, I've heard of people trying to make e-powers with connectors, and that doesn't work either. So it's just like, when you have to move a lot of current, you kind of have to, and the thing is, well, like SMD aluminum polymers, you can get them in ripple current ratings up to like 10 amps. So, you know, you can potentially you can have a lot of current going through those capacitors if you have them applied in such a way that that's actually necessary. And it's just like, well, if you bottleneck them with such tiny little connectors, that's not going to work. Anyway, other features on this card that are worth noting, which are on the front of the card again, is we have voltage read points over here, and also the PEX rail right here is that is controllable by software, and that's just a single phase VRM. And I couldn't manage to look up. This isn't actually a regulator. This seems to be a like a dual NFET in a kind of funky package. There's also a 10 amp fuse on the PCIe slot, which if you're going to put a fuse on your card, that's probably the only place I would put it, because if you're doing an extreme overclocking card and you put your fuses on the 8 pins, that's just like, yeah, you're just asking for those to blow up and really annoy somebody when they're on liquid nitrogen, because like either your fuse is going to be so big it's going to be useless, as in it's going to be for like 40 amps or something, so it'll never blow up, or it's going to be just big enough that it blows up when somebody pushes it on liquid nitrogen, and they're really not going to be pleased with that. So, yeah, good thing that they didn't put the fuse on the power connectors. But the PCIe slot, like this is actually something you might want to have a fuse on just in case. And yeah, I think that covers everything on this card. We've covered the it has dual BIOS, it has voltage read points. Oh yeah, software voltage control is possible for the entire card if you get your hands on Afterburner Extreme, which is a special version of Afterburner, which is meant for the Lightning cards and basically gives you like not unlimited voltage range, but enough voltage range that you can immediately destroy the GPU core, and enough power limit that you're not gonna hit the power limit. So yeah, that's kind of it for the GTX 680 Lightning. Like, honestly, I'm really glad I picked one of these up, because this, like, I didn't realize just how nice the PCB on these were, how nice the PCBs on these are, until I got it in my hands, and I was like, well, like, I knew it's a Lightning, and I knew like these cards are quite special, but I didn't realize that I'd be looking at, like, initially I was like, oh yeah, it's gonna have an 8-phase, and then it's like, wait a minute. That's one hell of an 8-phase. It's not just any 8-phase. It's quite the 8-phase right here. So, yeah, you know, really, really awesome card. Um, and it's a shame we don't see Lightnings built to these standards anymore. But at the same time, it's like, well, you know, if like I get it, I totally get it. It's not very cost effective to make cards like this and then not sell them. It's much easier to make cards with the names like this and then sell those. So, yeah, but that's it for the video. So thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with Actually Hardcore Overclocking, I have a Patreon and a Teespring where you can pick up things like Actually Hardcore Overclocking shirts and posters and socks and all kinds of other merch. Well, actually, that's pretty much all the merch. I just listed it off. Yeah, and if you don't want to buy anything, then of course there is the Patreon, and patrons get access to the AHOC supporters Discord, which basically gives you access to some like extra videos, and yeah, and it's a Discord server that I hang out on, but there's a lot of those, so you know that's not exactly like you get exclusive access to me. Anyway, so yeah, that's it for the video. Thanks for watching, and goodbye.